Okay, we are officially recording. Welcome to welcome to 204A. Um, Obviously, it's been an interesting couple of weeks since I saw you guys last. Um, just a couple of things. Let me get a couple of sort of housekeeping things out of the way. If you haven't used Zoom before, you probably will for quite a few of your classes. The university has a site license for it. Um, you are by default muted when you join. If you'd like to unmute yourself, you can do that either by holding down the space bar, or there's a mute button in the bottom left corner of your screen. So you can unmute yourself. I'm going to ask you to leave yourselves muted when you're not speaking. For the very simple reason that if everybody's unmuted, it collects a lot of background noise and it just makes it very hard for everyone to hear. A couple of other things. There is a chat window that you can access by clicking on the chat button at the bottom of your screen. That's handy simply because occasionally your audio will be weird or something will pop up, and this way you can send you could just send a text message like hello to everyone. You can also send that specifically to me if you want to just send me a message or somebody else in the class. The last thing that I'll note is if you click on the participants window, you'll have the ability to raise your hand. There's a raise hand feature. If I'm, doing what I do and just sort of yammering on, feel free to do the raise hand thing. It'll alert me, and then I know that somebody wants to ask a question. The audio is good on this, but not great. And so if more than one person tries to talk at once, it'll just be completely unintelligible. So we'll try to be fairly orderly about that. With that, I'll just say, welcome back. This is kind of ridiculous. We'll go over it a little more here in a minute, but so you're getting this class from not obviously in front of Kendall Hall. That has a little virtual background feature you can set up. I just have it set up because I'm tucked away in a bedroom, and it's better for you to look at Kendall Hall than it is to look at whatever's behind me. Okay, any questions about the interface, about using Zoom, how any of that works? All right, then we'll start talking about the class then. All right. Okay. So, let's see. That's not the one I wanted to share. Hold on. Let's try that again. I want that one. Okay. So, announcements. There are a lot of announcements for today. And feel free to stop me if you have questions, you need to clarify something, whatever. There is a course changes document up on Blackboard. You should read it. You should probably read it more than once. I'll give you the very quick version here. So there are 4 basic principles to how I'm approaching the rest of this class. Number 1 is this sucks. Like, we all hate this. Nobody signed up to take this class online. There's a reason we don't offer this class online. This is a terrible idea to try to teach intro mechanics online. And on top of that, you add in, all the uncertainty with the actual virus and the economy and people's jobs. And, I talked to one student from one of my other classes who's living in his girlfriend's parents' basement at the moment, right? I mean, everything's just crazy. So it's just bad, right? And there's really no way around that. Number two is this is what we have to work with, right? Independent of the fact that it sucks, this is what we got. I will do my absolute best to teach you the material. You will have to do your absolute best to learn the material. And it is not going to be easy. It wasn't easy when we were doing it under much better circumstances, and it's definitely not getting easier. Number three is that your health and your obligations to family and friends are more important than this class. There are all kinds of reasons to be concerned about life right now, and this class should be somewhere below those concerns on your priority list. After I wrote this and put it out, I learned that our college is not accepting drop requests until April 1st. That being said, I will support you fully in any drop request at any point up until you take the final for this class. If you would rather take an incomplete and come back and take it with me next semester, I'll support that too. The university hasn't worked out all the details on those options. Frankly, if I were in charge, I think the fair thing to do would be to offer you guys all a refund on your tuition, but they didn't put me in charge of that. So yeah. The last point I'll say is that the last sort of basic principle here is that we can't lower our standards for this class. 204A is foundational to most of your majors, and a lot of the courses you're going to take in the future, whether that's 204B or your statics class or, whatever's coming down the pipe for you, this class is foundational. If we cut corners here, it will, in the long run, hurt you because it will leave you unprepared to pass those subsequent classes that are coming down the pipe. So if you pass this class, it means you passed the class. It means I am as confident in your ability to do this as I would have been if we would done this in person. So those are the four basic principles. Beyond that, everything else is still somewhat up in the air. I've tried to think this through, but it is guaranteed that half a dozen things will pop up over the course of this semester that'll interrupt things and may require more changes. So let me just run through a couple of big changes. One is you need to regularly check your email, your campus email, and the course Blackboard page. That's our lifeline. That's how we connect with each other. Obviously, you all did that because you got here today, but be sure to just regularly stay in contact with your campus email and the course Blackboard page. The perusal readings. The perusal readings have not changed. You'll need to keep up with them. They are more important now than they were before because, frankly, the quality of the in-class instruction is going to go down. For the best that we try, it's not going to be as good as being in class, and so you're going to have to get the material from somewhere else, and that somewhere else is probably going to be the textbook. The homework. All of the homework is now on Wiley Plus. So homework 5, which was technically due originally the Friday before break that got canceled. If you did it, wonderful, but I'm not going to collect it. All of the homework now is through Wiley Plus. Many of you have heard me rant about online homework systems. I hate them. I think they are a bad deal. They're expensive. They're just a mess, but that's where we are. Now, the good news is Wiley Plus is free for the rest of the semester. So it won't cost you anything to access. The bad news is it still has all of the problems that online homework systems have. Online homework systems tend to emphasize the answer, the result at the end, rather than the process. And online homework systems often have interface issues, right? It's just frustrating. You can't figure out why it's not taking your answer, or if it, if your answer is wrong, or if your answer is just formatted incorrectly, or whatever, right? I'm sorry. Well, I'll do my best to help with those things, but to some level, that's just where we are. Okay, the other thing in Wiley Plus, we obviously don't have clickers anymore, and so at least some fraction of you will be viewing these recordings at a different time. So I'm not going to try to do clickers. What I'm going to do instead is we're going to use, Wiley Plus has something it calls adaptive practice. It's not bad. It's not great, but it's not bad. It basically keeps asking you questions until you get them right often enough that it thinks you've learned the material. So we're going to do that instead of clickers. They'll be weighted the same as clicker questions. Basically, a week's worth of clicker questions would have been. So that's the replacement for clickers. It's a poor replacement, but it's what we got. Okay, the next point is the labs. Obviously, we can't do labs over the internet, right? It's just not like, there's just no way. So here's what we're going to do instead. I'm going to call them video experiments. Most class periods, I will post a video on Blackboard of me doing some sort of experiments. Those are going to be limited because I don't have access to campus either. They've locked us out as well. So I just grabbed whatever I could out of our classroom and stole it. And, I'm going to be running this from, my bedroom or my garage or wherever. So there will be something. For each one, you're going to need to do a very brief lab report. Those will be individual. Obviously, it's hard to work in groups this way. You are welcome to talk with each other. You all have access to Zoom. You're welcome to post questions, have a meeting, exchange emails, right? So you're welcome to collaborate. I have no problem with that. But everyone will have to turn in their own self-produced lab write-up. So let me show you the first one of those. Let me come over here and let me show you how let me show you the course Blackboard page. That's probably actually the most useful thing. All right. Oh, no, I want this one. Okay, so this is what the course Blackboard page looks like right now. Actually, I'll put it in student preview so you can see the way you normally see it. Here's the changes document. You should have a read through that. I've added a discussion board feature. I have no idea if it will be useful, but it's there. I will check it regularly. You can post questions, comments. You're stuck on labs, right? It's just it might be more helpful than just bouncing emails around. So give it a try. If it doesn't work, it doesn't work. I don't care. Homework, we're not really using anymore. Experiments, that's where we're going to go to find these lab experiments. So here's the first one. It's just it's a cart on a slanted track with a spring, bouncing back and forth. Also up here, I've taken data for basically a little more than one bounce back and forth on that track. And this is, let's see here. Okay, so the the data file here, this is a Vernier graphical analysis file. So one of the things you'll need to do is you'll need to get a copy of that. It'll run on it runs on tablets, phones, Mac, Windows, you name it. But you'll need to download and install that. You'll download this file, and when you do, you will find that it looks something like, let me I got to change my sharing again. There we go. It'll look something like this, right? You'll have this lovely graphical analysis file that'll come up, and it's got, you'll notice it's got position, velocity, acceleration, and force. For this particular setup, there's an explanation that goes along with the video. But basically what you want to do, I want you to do two things. One, I want you to use this data to measure the spring constant for the spring. And then the other thing I want you to do is show that the work kinetic energy theorem holds for the cart as it goes between its lowest point and its highest point. There's a couple of things you'll need to do that. But basically what I want you to do is work this like a homework problem, right? Take a picture of it, drop it in a Google Doc, look at the data, you'll generate some graphs, you'll throw the graphs in, you'll have a little bit of writing, but pretty minimal. You don't need to write me paragraphs. And then you'll submit it. You'll submit it using our same lab submission form, but of course you'll do it individually, and you'll notice that that lab submission form has changed a little bit. Any questions about the experiments? Any questions about any of this so far? I feel like I'm just blowing through stuff, so feel free to stop me if you need to. Okay.
When are the experiments? When are the experiments due?
That's a good question. In theory, I'd like you to get them done, in the day or so after we talk about them in class, and I'll note them at the beginning of class. That being said, there are people viewing these delayed. So I'm not actually probably going to make a real deadline on those. I will warn you that if you let them all pile up to the end, that will go poorly.
Thank you.
No problem. Any other questions? I'll also note that the Wiley Plus assignments also have due dates. I am new to Wiley Plus, so I am still trying to figure it out. The due dates are mostly for your benefit. I will most likely, assuming I can figure out how to make the online system do what I want, I will most likely have them so they accept answers with no penalty up until the end of the semester. That being said, once again, if you leave them all to the end of the semester, this is going to go poorly. So I've got due dates in there at the moment. We'll see how that goes. Okay. Other things. Let's see here. Let me go back and share this thing. Okay. Exams. I have no good way to do exams online, so I'm not really even going to try. What I am going to do is I am going to have, so midterms, the midterms are canceled. The final exam is going to be an oral exam. What that means is you're going to sign up for a 15-minute block of time sometime on finals week. We're going to set up a Skype chat like this, and I'm going to give you probably a couple of problems, and you'll pick one and you'll just talk me through it, right? And the big reason for that is I just need to assure a base level of competence directly from you, right? If I could guarantee that nobody would cheat on anything for the rest of the semester, we wouldn't do this, but I can't. I trust you all. I don't trust the other members of the class. So I trust you. I just don't trust the other students. But that's the best way that I have figured out to try to do the purpose of an exam. Okay, quick question. Office hours. Office hours are, I'm still gonna try to hold office hours, probably using Zoom. We will see how that goes. One of the limitations that I currently have is that my home internet connection, it has a cap on the total amount of data I can use. So I'm not going to do office hours this week. The university is currently trying to find a way around that problem for me. But right now I'm going to try to save data as much as I can for the actual classes. That being said, email or the discussion board are ways to get a hold of me. And if there are other ways that we figure out to do this, we'll use those too. All right. Any other?
Nelson.
Yep.
Would it be beneficial if I were to hold some office hours once a week, twice a week, maybe?
That'd be wonderful. So, so there's one possible solution for the office hours. So Sean, if you could get me some times, and I'll post them on Blackboard and send them out by email.
Okay, will do.
Okay, let me make sure that I haven't missed anything that I really wanted to go over. Oh, a couple of other things. One is we are now completely and terrifyingly reliant on technology to make this all work. I am not very good tech support. I will try to be, but I'm not. And ITSS is currently completely overwhelmed with problems, right? I mean, every faculty on campus is in my situation, and every student on campus is in your situation. So we will do the best we can to help. The other thing I will add in is if you have accessibility concerns, you need to contact ARC. Again, they are completely overwhelmed, but that's their job. So you should get on their radar as fast as you can. I have tried to make things as accessible as possible. If there are things I can do to make them more accessible, please let me know. But yeah, we're sort of flying by the seat of our pants. Okay, the last thing I'll say, and then we'll actually get to actual physics. I am still working out the details of how these things will factor into your grade. So I'm going to just ask for you to be patient with me on that. I am not out to destroy everyone's GPA. Frankly, I argued forcefully that we should make all classes for the rest of the semester in the physics department credit, no credit. The dean shot that down. The dean says we have to actually give you grades. So we will give you grades. They will not be, the grades are not necessarily the most important thing here. I need you to pass the class. That's what I want. So, you know, we'll worry about grades in some way. So I don't know all the details on grades, but I will do my best to make sure the grades are not designed to hurt you. And we'll just have to figure it out as we go. Okay. The last thing I want to say is, and I said this before, is this is all my plan. There's a famous quote by George Patton, who is a World War II general, that said that no battle plan survives first contact with the enemy. This is absolutely true for teaching this class. I'm doing like 8 new things that I've never tried before. Some of them may work and some of them may fail, and we may have to change things around. But we'll just do our best. And we'll find a way somehow to make it through. Okay, any other questions about sort of course policies? All right. Good luck. You know, like I said before, basic principle number 1 is that this sucks. And so it's okay to, you know, not be a fan of this whole crazy thing that we're trying to do. All right. With that uplifting note, let's actually talk about physics. Yeah. Okay. One more thing I wanted to show you. I emailed this around. This is the flyer for how to actually get into Wiley Plus. Please let me know if you have any trouble with that. Again, I expect their tech support is probably a little overwhelmed at the moment too, because they made their service completely free to everybody last week, which means they're probably dealing with a big change as well. All right. So now we get to actual physics. So here's your not really a clicker question, but we'll call it a clicker question for the day. So we have a polling feature here on Zoom, and I am just going to make a quick thing here. And I hit save. Oh, it's making me do things. Okay, so what I'm going to do is I'm going to launch a poll, and I want you guys to take a look at this question and choose A, B, C, or D. All right, I'll give you another 15 seconds. All right. Last call. Okay, so if I share results, there we go. So you can see the most popular choice is B. That's correct. Power is the derivative of work with respect to time. And we'll talk a little more about that here in a second. So let's see. Now I'm going to try to do something that we will see if it works. So my attempt at getting a whiteboard to work with this thing is this. Let's see. Oh, wait a minute. That's not going to work because I got the background going. Nuts. Okay. Fun. Now you get to, listen to me change things. There we go. Okay. Aha, now you can see my lovely piece of paper. Okay, so when we talk about work, so work is the integral of force over distance, right? And it turns out that work is a fairly useful concept. We're going to use that a lot. But interestingly enough, when you build a motor, most motors actually tend to they don't produce constant force in time. They don't produce a lot of things. What they do produce roughly constant amounts of is something called power. So power is just defined as the time rate of change of work. It's the rate at which something can do work. So, so if we carry that through, right, we end up, that's the derivative of the integral of force over distance. Now we have to be careful because the derivatives with respect to time and the integrals with respect to space. And so they don't cancel each other out, but we can do some interesting things with them. For example, if it's a constant force, right? If force is a constant, so for us in this class, that means everything except a spring right, then our work is just force dotted into our distance vector, our displacement vector, which means that power is just the derivative of force dotted into distance. And remember, we said that if force is a constant, then that can come right through the derivative, and we just end up with force dotted into, oh, I used D twice. That's probably a bad idea. Okay, let's not call it D. Let's call it X. There we go. And this, you should all recognize, is velocity, right? So if force is a constant, right, that's important. If force is constant, then your power is just the dot product. Oh, not a vector. Power is just the dot product of force and velocity. So that means that it can that power can apply a force over a distance, right, that is changing in time. So this leads to some interesting things. If they're in the same direction, right, then we don't have to worry about angle. It's just the magnitude of the force times the magnitude of the velocity. And oftentimes they will be, right? If we talk about motors usually have forces in the same directions that they're moving. But you get some interesting cases where you're going to have, for example, if you have a motor that is pushing not in the direction it's moving, which, for example, often happens in boats or other things that can sort of slide around corners, you can get some interesting things there. But really, the point here is that force or power is really just the rate at which you can do work, right? It's how fast can you do work. So more power means you can do work faster. Less power, of course, means you have to do the works more slowly. Which is why when you talk about motors, there's usually two numbers that matter, particularly if you're talking about engines for trucks or things like that. They'll talk about the power, which is often reported in horsepower. That's a lovely historical oddity because when people started developing cars and tractors, they were competing with horses, right? And so they wanted to find a way to demonstrate that this newfangled truck that I just invented is the equivalent of like 15 horses. But the SI unit for power is the watt, right? And 1 watt is the same. If you just look at the units here, it's 1 Newton times 1 meter per second. Or if we take those apart a little further, a Newton is a kilogram meter per second squared. So a watt is a kilogram meter squared per second cubed, right? Which is not a very helpful unit, but it's always nice to know how you break it down. Okay, so that is fundamentally what power is. So when we talk about the ability of an engine to do work, right? Power is one of the things that we really care about. Power that tells you how fast it can add energy to things. Now, one other thing I want to point out here, right? If you remember our work kinetic energy theorem, which we were talking about before all this crazy happened, the work kinetic energy theorem says that work causes a change in kinetic energy. So it's the final kinetic energy minus the initial kinetic energy. Well, that means that we can also think about that in terms of power, right? Because power is just the time derivative of work. And let's see here. Yep. Power is just the time derivative of work, and which means that it's we could think of it as if we think of the initial kinetic energy as a constant, right? That's just whatever you started with, right? Well, then that doesn't matter at all, because when you take the time derivative of a constant, it just goes away. So what this is saying is this is the rate of change of the kinetic energy of an object, right? The power applied to the object, right? The power that's doing work on the object is going to change its kinetic energy, right? We can take this apart further, because kinetic energy is just 1/2 mv squared, right? So we get the derivative with respect to time of 1/2 mv squared. Usually your mass is a constant, doesn't have to be, but usually it is. So what this leads to is it leads to 1/2 an m just coming right through the derivative. And then all we have to do is take the time derivative of the velocity squared. Now, be careful here, because in our case, velocity is a function of time. So we're going to have to chain rule this thing. When we chain rule this thing, we get that power is, we still have that 1/2 m floating around, right? And then when we take the derivative, we get 2v dv dt, right? Which means that if I work this all out, I get 2 times 1/2, which cancels the 2. I get the mass, I get a velocity, and dv dt is just acceleration. So I get mass times velocity times acceleration. Okay. So the point of all this is simply that we've just manipulated the definition of work a few different ways in order to there we go, I'm back. We've manipulated work a few different ways in order to get some things that might be helpful. Now, you'll run into a couple of questions on the Wiley Plus homework, and there were a couple on the written homework that I'm not going to collect, unfortunately, that got into this idea of how you can use power. Okay, so this concept of power, as I mentioned before, it's actually, physicists don't use power very often. It's not really a fundamental concept. It's sort of this weird thing where you've got a quantity defined in terms of an integral, and then you also take a derivative, but not with the same variable. So it's kind of this weird thing. But like I said, it turns out that a lot of motors and engines produce roughly constant power. So for all you engineers out there, it's a useful thing to talk about. All right, so here's your next poll question. How long would it take a 100-watt motor to lift a 10-kilogram object 10 meters? And let me figure out how to deploy the poll. Stop sharing that. And I'm just going to relaunch it and clear the existing results. Maybe. There it goes. All right. So answer this one.
Hi, I can't see the poll.
You can't see the poll. Okay. I'm not sure how that works. Can any, no, nobody can see the poll. Nobody's voted. Can anybody see the poll?
No.
No. Okay. Well, let me try to end it and close it and start again. Can you see it now?
Yep.
Great. I'm not sure what I did differently the second time, but we'll call it good. All right, I'll give you another 15 seconds and then we'll shut this one down. All right, let's see. So, okay, let me go back over to my dear friend, the document camera. And there we go. Okay, so this problem, what we had said is we've got some object, right, that weighs 10 kilograms, and then we want to lift it 10 meters, and we got it hooked up, you know, probably over a pulley or something, but in this case, it really doesn't matter, right, to some kind of motor here that can do 100 watts of power, right? And if you remember from our previous stuff, there's a couple of things we could use here, right? We could just figure out how much work it's going to take to lift that thing, right? Now, we do need to be careful here because there are two forces doing work on this crate as we lift it, right? There's the motor lifting it, and then there's gravity pulling downward on it, right? So if we draw the free body diagram for this thing, we've got, we'll call it the motor force, right? And we've got gravity going downward on this thing. And so, but we know it took, this thing can do 100 watts, right? So 100 watts, right, our power is just defined as the time rate of change of our work, right? And in this case, we have this nice feature that the force is going to be constant. How do I know the force is going to be constant? Well, because the whatever we're pulling up with, right, is just the same as whatever's gravity is pulling down with. And so if the force is constant, we can use all those handy dandy formulas we had before, right? So because the force is constant, because m is constant, we can figure out here that your power is just the magnitude of the force. Oh, it's constant and it's in the same direction. As the motion, right? That means that that is just the magnitude of our force, right? Which in this case, I shouldn't write F, is M, right? The big M, the motor force, times our velocity here, right? And I can further help myself out by figuring out, by I know that it went, the velocity here is just going to be, right, that 10 meters divided by my time, right? Which is what I want at the end of this thing. Okay, I know P, I know 10 meters, right? I know the distance, right? I broke one of my own rules. I put a number in. Bad me. I'm going to make this, we're going to call that D, right? Okay, but now I got to deal with this guy. I got to deal with this, this force. And the way I can do that is to come back up here and look at this free body diagram, right? If we're just moving upwards, right, M and G have to balance each other. Otherwise, I'd get an acceleration. So what that means is that my M here, right, if I write Newton's second law, a zero acceleration is just equal to M minus G all over the mass of the box. But the mass of the box is just going to cancel, which means that M is just equal to gravity, which is equal to the mass of the box times 9.8. 9.8 is really close to 10. So we'll just make our lives easier and call it 10. And if I put that all back together, I get that my power is the mass of the box times free fall acceleration due to gravity times the distance it went all over the time. And if I rearrange this a little bit, right, I take time over to this side, I take power over to the denominator, I get that the time it takes is just the mass of the box times the free fall acceleration of gravity times the distance all over the power, right? This is 10, that's 10, that's 10. So this is 1,000 divided by 100, which means that my time is going to be 10 seconds. All right, how are we feeling? You get to do, there's a reaction button. If you guys want to give me a thumbs up, I don't know. Does it have a thumbs down option? Can you give me like a boo, throw things at people? Should have an angry option. All right, well, if you have questions, let me know. Okay. So let's, I see some thumbs up. That's good. It really should have a thumbs down. Okay, let me come back over here and we'll go back to this thing. Okay, so our next point that I want to, well, let me actually take a step back real quick. When we talk about power, right? We usually are going to use power in the terms of some energy source. Something is generating work, right? So here's an example of that, right? We're riding a bike on a level road at a constant speed of 15 meters per second and experiencing a drag force of 95 newtons opposite my direction of motion. How much power must you generate to maintain your speed, right? So this is the basic problem of riding a bike, right? This is why it's work to keep riding a bike, because you're constantly experiencing a drag force. Cyclists go to great lengths to try to reduce this drag force. That's why you see cyclists wearing those like weirdo tight, like, you know, shirts and pants and stuff. You'll see cyclists do all sorts of things with their helmets, right? They'll have these like crazy helmets that that are, you know, aerodynamically designed to try to reduce drag. Because, you know, for a good bike, that's the only real force slowing you down. The friction is very, very small in terms of what it actually does to give you any trouble. So all you really need is drag. So for this one, let me just walk you through how I would set it up, and then I'm not going to solve it for you. I'm going to leave this one for you guys to work through. And then actually, if you want, you can either you can post your solutions on the discussion board in Blackboard. Okay, so let me go back over here. Where did we go? All right. And okay, we're already there. All right. So for any type of energy problem, we're still probably going to need to know forces. So don't forget to make your free body diagram, right? You should still draw a free body diagram. You should also probably draw something that, you know, sort of outlines the problem. Here's my stick figure on a bike, right? He's got really long arms. Back off. All right, so there's my stick figure on a bike. Stick figure on a bike. What forces are acting on him? If we wanted to draw a free body diagram over here, we've got, of course, we've got a normal force from the road, right? And we've got his weight due to gravity, right? But those actually aren't very important here because remember, we're riding on a level road at, you know, we're not jumping off the ground. We're not flying through the air. Okay, so he's got to have some force going forward, right? And he's got to have some force going back. Now this force I'm going to call D for drag, right? That's the air resistance, you know, the pushing through the air that he experiences. Now here's the question: what is this force? And really what that is, that's a friction force, right? That's a force of friction between the guy's tires and the road, right? Because the tires are pushing backwards on the road is pushing forwards on the tires. Now, where does that force come from? Well, it comes from the guy's legs turning the pedals, which I don't have in my drawing, but you can imagine pedals. Here, we'll draw. No, I don't even try. Okay, his feet are pushing against the pedals are pushing against a gear, the gear's pushing against a chain, which is pushing against another gear, which is pushing against the structure of the wheel, which is pushing against the tire, which is pushing, right? It gets complicated. The point here, though, is just from if we think of this as all moving together, all it is a friction force, right? There is some amount of friction here that is balancing, that is pushing the bike forward, right? And it's balancing out that drag. I know it's balancing because he's riding at a constant speed, which means his acceleration is 0, right? It's 0 in every direction. Okay, one more question, and I won't answer this, but I'll leave it for you guys to ponder on. And if you get stumped, shoot me an email or post it in the discussion board. What kind of friction is this? Is this kinetic or static friction, and how do you know? Okay, so our acceleration is 0. We know that these two forces balance, right? Because acceleration is 0. And we know that these two forces balance, but we don't actually care about them so much. So we're just going to think about drag and friction, right? Which means that our acceleration in the x direction is just friction minus drag divided by the mass of the bike, okay? A couple other things that I should put on my diagram. We know his velocity, right? His velocity is 15 meters per second, which is about 30 miles an hour. So that's a pretty good clip for a bicycle. And the drag force has a magnitude of 95 newtons, right? By the way, these are actually fairly realistic numbers. If you know Dr. Ayers, he's the department chair in physics. He is a avid cyclist, and so I actually got him to give me actual numbers for these problems. Okay, so if we come back down to here, that equation, if we solve it for the friction force, simply says that the friction force has to be equal to the drag force, okay? That friction force fundamentally has to come from the rider. Now, here's where it's useful to talk about power as opposed to talking about force. All this gear stuff in here that I didn't draw, right? All that gear stuff involves changing forces, right? It involves, because if anybody who's ever ridden like a 5-speed bike knows that as you change the gear ratios, you change the amount of force needed to turn the wheel, right? You change the amount of force and the distance, right? The distance in a circle that you have to push around that force. But here's the cool thing. When we're talking about power and work, we don't actually care. All we care about here is how much force was required out here and how fast we're going. Because if you remember, if we go back to our definition of power, right? Power is the derivative of work with respect to time. And in this case, again, our force is constant, right? Because we're moving at a constant speed. We know we have no acceleration. The drag isn't changing. So we can simply write this out as this is going to be the force dot, not W, the velocity, right? Our power is just our force dotted into our velocity. And it's even easier than this because force and velocity are in the same direction. So our power is just force times velocity. And if we plug in the numbers, you can figure out what the number is, right? 15 times 95. I don't know what that comes out to, but you know, it's a number. Okay, I just realized I solved the thing, which I told you I wasn't going to do. So, you know, great planning on my part. But you get the idea, right? You get the idea that what we want to do here is we want to, we really want to set up our picture, right? Our free body diagram, use Newton's second law, not to solve the problem, but to make our lives a little easier, and then look at the power, right? So anyway, this number, if you work out this number, right, this number is going to come out to like several hundred watts, right? Which is a lot of power. A few hundred watts is a lot of power. Generating that for a long period of time takes a lot of work, which is why cycling is good exercise. Okay, questions about any of this? You feeling good? Okay. All right, let's do one more here. Let me come over here. Oh, no, that's the wrong thing. Hit share. And let's do one more example. And this one is a little bit interesting because this gets into that definition of power we used when we talked about kinetic energy, right? So a car engine produces roughly constant power, not force, right? A car engine, it turns out, doesn't produce anything close to constant force, but it does produce roughly constant power. It's actually not quite constant. If you know anything about car engines, you know that you get more power with more RPMs, right? The faster your engine spins, the more power you generate. But ballpark, it's a fairly constant number if you're shifting gears properly. For a Lamborghini, you can have a car with a mass of 1,900 kilograms and an engine that can produce 510 kilowatts of power. And what this question is asking us to do is find the position, velocity, and acceleration of the car as functions of time. So again, we're going to have to come back over here and look at this. I wish there was a way we could keep this up for both of you to see. Anyway, let me just switch to the other camera. All right. Oh, no, we're there. Okay, so remember we had our car, right? This is not how a Lamborghini looks, but you get the idea, right? And we know that it has a power, the engine can produce a power of 510 kilowatts, right? Which means 510,000 watts. And that our car has a mass of 1,900 kilograms, okay? And we want to know the position, velocity, and acceleration of the car. I didn't say this in the problem, but let's assume it's starting from rest, okay? So if you remember what we did, we said that power is the time rate of change of work, right? And we use that work kinetic energy theorem to say then that that's the time rate of change of kinetic energy. And we work that out to say it's the mass times the velocity times the acceleration. So this can get us to things we want, right? It's got velocity in here, it's got acceleration in here, but we've still got two unknowns, right? We don't know the velocity and we don't know the acceleration. So what do? Well, it turns out what we do is we take a step back. Instead of going all the way to here, right, we recognize we're going to want to go to here, right, eventually. But instead of going to there, what we're going to do is take a step back over here. And we're just going to write this as the time rate of change of kinetic energy, right? And now, instead of taking the derivative of kinetic energy, let's undo this derivative. And we can do that if we take an integral of both sides with respect to time, right? The time integral over here will undo the derivative. So over here, we'll just get kinetic energy, right? And over here, we will get the integral of a constant, which we know how to do, right? So that means our power is just going to look like power times time. And voila, we've got the velocity as a function of time, right? If we solve for velocity, we get that, we get 2 power times time over mass equals velocity squared, which means that our velocity as a function of time is just the square root of 2 times the power times time over mass. Okay, that gets us to velocity. Now, where do we go from velocity? Yeah, I can put the problem back up on the screen here in just a minute. So that gets us to velocity, right? Velocity is good, right? But now how do we get from velocity to the other two things I want, right? Which I wanted position and I wanted acceleration. Well, the answer is we just do it the same way we did before, except for now I'm making you take slightly harder derivatives. They're not actually that much harder because I can rewrite this thing as some constant, square root of 2p over m times time to the 1/2 power, right? So what's the derivative of this thing? Well, its acceleration is just dv dt, right? Take the derivative of this thing. I take this half down to the front here, and I subtract 1 from the exponent. So that means I'm going to get 1/2 times the square root of 2p over m times t to the negative 1/2 power. Which means if I clean that up a little bit, I get the square root of p over 2mt, right? Putting that all back under one radical. And similarly with position, right? That's just the integral of velocity with respect to time. Well, taking the integral of this thing, that constant it doesn't do anything, right? But I do have to deal with this guy. So I'm just going to pull the constant right through the integral. I've got the integral of t to the 1/2 with respect to t. That comes out to, there's my integral, here's my constant still. I have 2/3 times t to the 3/2 plus a constant, right? I should put these all in parentheses. Plus a constant here, which I'm just going to write as c. Okay. Now make sure you understand what I did here with the 3/2, right? It just has to be whatever comes down to if we took the derivative of this, we'd bring this down and it would cancel the 2/3. Just make 1. Okay, be careful with this constant too. This constant actually isn't our initial position, but this constant times this mess would be our initial position, which I'm going to say is 0. So that means our position as a function of time just looks like 2/3 times the square root of 2p over m times t to the 3/2. Okay, I want you to think about these for a minute. And actually, this might be a good exercise to work on by yourself. You should graph these functions, right? You should graph this guy, your velocity, that guy, your acceleration, and this guy, your position, to see if they make sense, right? Because anybody who's ever driven a car knows that you get a lot of acceleration right when you start out, but as you go faster, you get less acceleration, right? And that would seem to be consistent here with having this t in the denominator, right? This function is going to go down as t gets bigger. So anyway, that would be a good thing to play with. Okay, let me put the question back up for a minute here. So there's the question we were working on. And I'll give you a second to chew on that. Okay, so just to review, I'm going to stop sharing this thing and just come back and see my smiling face. Just to review real quickly, the key concept today is this definition of power. That power is the time rate of change of work, right? Power is the rate at which something can do work. So it's really the foundational concept here is really work, right? That work is the ability to change the kinetic energy of an object, right? It's the ability to apply a force over a distance. And that power can sometimes be a useful concept, particularly when we're dealing with engines, right? Whether those engines are a person riding a bicycle, a car engine, a motor lifting some object, because many of those things have constant power where they won't have constant velocity or constant force or constant a lot of other things in these systems, but they may have constant power. Okay, with that, I'll open it up. If anybody has any questions, we can do questions for a minute. Yeah, and then I'm gonna turn off the recording here once we're done, and hopefully see you guys all back on Friday. So questions, anybody? Okay, then we'll stop there. I am not, so this, this class went a slightly shorter than I had thought it would, but there's no reason for me to just keep you here, dancing and whatever. So the actual length of these classes will vary. That's what I'm trying to say. Basically, I just have some material that I feel like we need to go over. Once we've gone over it, we'll be done. You've got a lot on your plate in terms of other things to try to keep up in the class. So I am planning on posting this video immediately after class. Sometimes it does take a little bit of time to process, both on the Zoom processing the video and YouTube. I'm using YouTube to post these things. But I should have it up within a couple of hours after class. Any other questions? We feeling good? All right. Well, hopefully this doesn't suck as bad as you or I feared it would. But everybody wash your hands, and I will talk to you guys all on Friday. Have a good couple of days.